Okay, so this is our definition of the angular momentum. Okay, and this is a material property, more a material geometrical property of the object. It's material because also we have the density. We should have here density, which is not written because if in case that it's not homogeneous, it needs to be integrated for all each density in the body. So there is also one remark here. So stating how this double vector, so this is like one matrix and another matrix. This is what we saw yesterday. Okay, this matrix is such that if we multiply this matrix by a vector, we get the cross product. Okay, so that's a matrix. Sometimes I put double underline in order to indicate this that it's a matrix, and one underline to indicate that it's a vector. So there is one property of this that I would stated in the slide. The double product of this matrix, it's equal in fact to R by RT, okay, minus RTR and identity. Okay, so this is a scalar, so you can check that this is verified for that matrix. If you multiply by itself, you get also RT, so it means that this component ij that we have here is equal to Ri ij, okay, and minus the sum of all the components from 1 to 3, okay, the vector by itself by delta ij, by the identity tensor, right? So in doing that, we would obtain that our inertia, which is minus this product, okay, the component ij is nothing else than rkk, okay, minus ij, okay, and here only whenever we are in the diagonal terms. Okay, so that's because we have this minus here. Okay, so this is the integral, okay, of this expression integrated and by the density. As I said, we need also this density here for the body. So for a case like this one, let's imagine that we have here direction 1, direction 2, and direction 3. Okay, so if we want to compute, for instance, component 1, 1 of this inertial tensor, and we have it, okay, already aligned through the axis of symmetry, okay, of this body if rho is constant. Okay, we will have rho. In that case, that is so the sum of the 3, 1, 1, 2, 2, and 3, 3, minus the 1, 1. So at the end of the day, we would have R22 plus R22, I mean R2 by R2. Okay, R2 squared plus R3 squared by the density, that if it's a constant gets outside, and this integrated on the body. So we see that this is the integral for each our body, for each position of how our mass is distributed along. If this is a cross section of our body, so in fact it's just the 2 and 3 components. So for each cross section, it tells us how is the integral of the square of the distances that we have here. So it tells us how the mass is distributed away from this axis 1, in the case of component 1, 1. Okay, if we would like to compute omega 1, 2, so in that case, just following this equation that we have, or in this case, what we also have here, we have the same integral on our body. This is not 3, so on a body, and we will have, okay, not distance because we are not in the diagonal, and just 1, 1, 2. Okay. So it means it's the integral on all the positions given at position 1. We're going the integral on all the 2 components. If it's an axis of symmetry, in fact, what we will have, okay, is that the integral of R2 is symmetric, so that would give us equals to 0 if axis of symmetry. Okay, so when we compute this tensor with respect to the axis of symmetry, we get that is diagonal, and on each diagonal term, what we have is the distribution of the mass around each one of the axes, 1, 2, and 3. Okay, so this is the idea of this tensor of inertia, right? Then, if the angular momentum, in fact, is this is the rotation, but seen in this axis with respect to the reference. Well, we said that we have in our reference of the body, we have this angular momentum, and in fact the body maybe is rotating and have another orientation. Okay, but the angular momentum can be computed as this omega in the frame of these of symmetries of the body, and the angular momentum also seen referred to that frame. So we have this this definition, okay, all in the body frame. Then what we have is how, what then we have is the angular, also the same angular velocity, okay, how it's rotating, okay, but rotated because now we want to express this W in the space in our frame where the body is really located. Then we have these some properties of this rotation matrix. These are SOCs, orthogonal matrix, so it means that the inverse is equal to the transpose of the matrix. And we will have time derivatives because our equations of motions have time derivatives, and this can be computed as this W hat. This W hat, in fact, is the same as the cross that we had before. Okay, in fact, here we could have R hat also. We have this hat is an operator that is as the angular velocity, okay, the vector product of omega, okay, and expressed in matrix form. Okay, so in fact, how this rotational matrix, the derivatives. So what we see is that when we work with rotations, things are a little bit complicated, and precisely because of this time derivative. We have that R. The whole complexity of dealing with rigid bodies is that we have a rotational field, okay, which includes this omega or the capital omega, okay, and this is related through the rotational matrix. But R belongs to SO3, but instead R dot it's equal to this omega hat by the same R, okay, and now this does not belong to SO3. This is a matrix, a product of two matrices, but the transpose is not the inverse. Okay, so in vectors this was not happening. U was belonging to R3 in our case, and our velocities U dot also belong to R3 and all the derivatives. With matrices and with rotations, in fact, like this orthogonal set, so we have that in fact our kinematics has a certain structure, but the time derivatives don't. Okay, and that is a little bit of a complexity when we want to interpolate things. Okay, to interpolate we mean to have mean values in time. Okay, we have this omega n plus 1/2 that we may do, or increments of omega, so things are not that simple, and that's where the complexities of the algorithms rely. So now going to the equations of motion, we have the kinetic energy is defined as, in fact, the kinetic energy, we could have it as the integral of, with respect to our body, and that is rotating. Okay, we have this rotator, and then what we have is the same way that we had before, that is the mass for a particle by each square of the velocity. We would do exactly the same thing here. Okay, we have a position, but we need to integrate. We have this density field, so we will need to have a density and a velocity. Okay, so the density by the velocity of each point, and that integrated, and the velocity squared. Okay, and integrated on the whole body. Okay, so it turns out that this, if you do the integral and express your velocity as with respect to the center of mass that of the particle plus the velocity with respect to that point for a body that is rotating, you get this expression in here, which is another scalar. This is a vector. Okay, so it's our tensor multiplied by the vector and dot multiply before. Okay, so we can reach the same expression in terms of this inertial mass. So it has also the units. This is the integral of quantities to the length squared integrated on a volume. Okay, that we have. So in fact we end up having the quantities to lengths to the cube here. Okay, and then we will have this velocity. So in fact we'll have the same units that we will have like a mass and multiplied by velocity squared. So the same thing here. W doesn't have units, so W talking about units will be radians per second. So second minus 1. Okay, so this mass is the mass, and we have then the length square that we have is what we have for the units for the tensor here. Okay, integrating that mass square but being integrated, so we end up having the same beta squares, and by the also by the density that we will have there. Okay, so we have that, and then we denote this by the relation between the small omega that we have and the real one, and with respect to the body or not. So small omega it's r by omega, so r minus 1 it's equal to the r transpose. So big W it's I'm calling W sometimes erroneously having omega. This is a W that we have here. So we have capital for the body frame and small for small W for the one referred to the spatial coordinates, to the spatial angular velocity. So this is R transpose by W. So if we do this change here, we will have W transpose by RT omega R and a small W again. Okay. So we, by doing this change of variable, what we have, and we use Euler-Lagrange equations in the same manner. Remember that they had Euler-Lagrange equations were the time derivative of the derivative of L with respect to our Q dot, which in our case now are these omega that we have. Okay, we don't have any elastic energy because it's a rigid body, so it does not deform. So our Euler-Lagrange equations are simply stated like that, which since L is equal to remember that was kinetic energy minus elastic energy. In our case for the rigid body, it's just T. So in fact, is the time derivative of T with respect to our omega. This should be equals to 0. Omega small w, shorter to say omega that small w. All right, so these equations we end up having that the time derivative of this quantity with respect to small w, it's nothing else than r omega and omega. This is a quadratic form with respect to small w. So the time derivative is 2 times r omega r transpose w, which is in fact our r omega multiplied by capital W. So this is our Euler-Lagrange equations that we need to solve. So basically our equations should be the time integration algorithms that we had. Now instead of having velocities, we have this angular velocity, and r also, that is the orientation, which is also changing. So this theta is how it changes. So any position, any rotation of a body can be stated as a rotation around a fixed axis, and so it means an axis and an angle, and this is what determines this r, Okay, this also then depends on theta, and so we have this r in fact depends on theta, and we have that r dot is equal to omega dot, okay, this vector, well, theta omega dot by r. So this depends on our theta, and the relation with omega and theta, okay, is not exactly the time derivative. Okay, so we just need to keep in mind that this is not exactly the time derivative of this vector theta. We know that the way to parameterize rotations it's a little bit a long story, but just to keep in mind that this r depends on my theta, and this is the angular velocity that we have, okay, rotating the body, okay, at the moment around this axis. Okay, so the complexities, we won't go into the algorithms, okay, but just to know, okay, that the time derivative of this is like the angular velocity, angular momentum, okay, in the body frame. So what we have here is the total angular momentum in the spatial frame. Okay, so this should be equals to 0. What we have in parentheses is r, okay, of our angular momentum. We have this j, which is the same angular momentum that we had before, and this can be stated as the time derivative of the spatial angular momentum, okay, which is the angular momentum with respect to the spatial frame. In fact, the Cartesian and inertial frame, one that is fixed, is not moving. The frame of the body is moving, so it makes sense that the angular momentum, okay, this vector is not going to change. This is the actual Euler-Lagrange equation. What they are stating is that there's no change in angular momentum of a body. Right, so this should be equals to 0. So it means that r dot by omega, we do the time derivative of this term, plus omega, and here we have accelerations, which is the time derivative of our angular momentum, and this should be equals to 0. Right, so these are the equations that we need, and for that we need to state how we parameterize that. Okay, how can we parameterize this vector omega that we have? Okay, r dot we said was small omega by r, or r by okay, this hat here multiplied by the same w, capital 1, plus r, this inertial tensor, and by capital W dot. Okay, so now with that, that's what we need. How do we interpolate? Which is the time derivative? Shall we do omega or W, I mean capital W dot equals to, this is going a little bit slow, so this should be this interpolated like that. Okay, so in general it is not, and also we need to interpolate what is our orientation. Okay, so we have a matrix at time n plus 1, and we have a matrix at time Rn. Okay, is it n plus 1 half the average of the two? So if we do the average, divided by delta t, this does not belong, this is not a rotational matrix. Okay, so in general this is not the way to proceed. So you don't do this averaging, and you also don't do this averaging for the velocities. Well, with respect to the vectors you can do, okay, but not with respect to the rotation. So what you may do is stating my axis, so the rotation that we have, which in 2D was this cosinus and sinus matrix, which this depends, okay, my rotation at time n, it's equal to theta n, and I want to, my rotation at n plus 1 would be my rotation with respect to theta n and theta n plus 1. So what I might do is, having quantities defined at different times, doing the average here, and then having r plus 1/2, not defined like this, but as a rotation at theta n plus 1/2. Okay, how you go from theta to the rotation? So there's different ways to parameterize. Okay, this theta, as I said, is what is this axis. This is the rotation of that body, and so give me a fixed axis around each around which is rotating the body, and theta is the amount of the rotation that we have, right? So there is this expression which is exponential of theta hat, which is in fact you get the exact value, okay, of the rotation matrix, and that's how what we would do here, okay. But the exponential of given a body when it rotates and goes to another orientation, okay, means that there's a fixed axis, okay, and how much it rotates around this axis, so would be theta. So given this vector, I can build my theta hat, which is this matrix, and then compute the exponential of this theta hat, which is like the Taylor expansion of theta. It can be computed as this plus theta divided by 2 square plus etc. Theta, this matrix, multiply n times by itself divided by n factorial, etc. So the exponential understood as this series here with this matrix, instead of 1 having the identity. And with that, you would get the your rotational matrix, right? So you can do and you work with these angles. Okay, so just to indicate that there is also time-conserving algorithms, time-conserving algorithms and angular momentum, time-conserving, I mean energy-conserving and angular momentum, which means that my j at n plus 1 is equal to j at n. Okay, or said otherwise, that my r n plus 1 by j capital measured in that way, it's equal to the same that I had at time n, okay, in the body frame, and this j is omega, okay. So preservation of angular momentum means that this is my inertia, okay, that I have multiplied by omega, okay, at n plus 1, it's equal to rn by my this does not depend on time. Omega omega is constant, but the angular velocity is not. Okay, so we will not have this term here. Okay, so there's algorithms such that you interpolate your rotations and your angular velocities in such a way that they preserve this identity. That would be preserving angular momentum. And preserving energy means also that they preserve our kinetic energy. The only energy that we have is a kinetic one. So it means also that our 1/2 of omega 1 by this tensor by omega 1 is equal to 1/2 of omega n, our tensor, and wn. Yeah? And with a strain and with a moment of inertia tensor. So that would be angular momentum preserving, and this is energy preserving. Okay, so you have interest in having these quantities. This is very an algorithm that does not preserve the angular momentum, so you see that your body may be starting to be tilted. Okay, so it's rotating, and bit by bit is drifting from what you see what we'll be doing. Okay, and also the energy, if it's not preserved, so there may be that its rotation increases or decreases. Okay, also with respect to a fixed axis, for instance. Okay, so the just complexities due to the rotations. They're the bottom message that we have for rigid bodies. Okay, preserving algorithms, they were They were designed, in fact, in the 90s. Okay, applications that you may have, if you want to gyroscopes, okay, or gimbals, so that you have these uh, rotating bodies, may have that you assume rigid, and all kinds of other applications. Spider cam is a camera you have in the football stadiums, which that it moves from one side to the other. You consider that as a rigid body, but it has some pulleys that needs to be also modeled. Okay, so you're interested in having this, and gyroscopes do many fancy things. Okay, when you the conservation of angular momentum, which is just preserving this quantity, has some weird implications. Okay, when you have a body rotating and you turn it, okay, so you create a turn in another direction. Okay, by the preservation of angular momentum, and um, and you are well interested in having that well modeled. Okay. So with that, we finish the rigid bodies. Okay, without going into detail on the algorithms, but because we want to see also other cases. Okay, going back to the particles. So we want to see in reality you have friction, and friction we mean any load that is proportional to velocity. These are viscous effects or aerodynamical effects. Okay, you have a body that it's moving, and because the body is not in the empty space in general, so you may have a fluid, and the interaction of the particle with the fluid, one of the basic interactions is stating that you have a frictional force that it's the opposite direction of the velocity it's moving, but with a given coefficient c and proportional to the velocity, right? So that's what you would have if a mass or a particle is falling with a given velocity. So it turns out that we have gravity in here, so we will have that mass by acceleration. If we have x oriented like this, so we have mx double dot should be equal to the external forces, to the gravity that we have. Okay, so rho by g. Okay, so if this is constant, it would be accelerating every time we have this different from 0, and our acceleration would be this rho divided by m and according to g. Okay, so we want to in fact this rho in this case for this particle would be equals to m, so we have mx double dot equals to mg. So in fact our acceleration will be exactly our g. This is with no friction. Okay, we have friction. Of course, this is not the real case. Particles, they don't keep accelerating infinitely when bounded, but we have an additional force that we may be that our mass by the acceleration plus some force proportional to a given friction coefficient c, and that would be as if we would have external force equals to c by v. Okay, so this changes our result, stating that x is bounded. Okay, so our final velocity that we have as a function of time, so it would be start increasing, but at a given time it is stopping our body from having increasing velocity. In this case, our velocity would be the acceleration is constant, so the velocity will be with a constant slope, linear. Okay, if we start at rest for a given t0. So instead of that, it slows down particles. In our case, we apply that in order to simulate what may be happening when this is embedded in a fluid. So this introduces some non-conservative forces. By non-conservative, we mean that if it goes around, this is fixed, and it goes around with a certain path and goes back to the position, okay, then if there are no frictional forces, we would have again the same elastic potential for that mass, but in this case, by the path determines a different potential here. Conservative forces are those that depend only on the position. That's our U of L, okay, that just depends on L. If L is at a given time goes back to the same position, so our force due to elasticity, it's minus the gradient with respect to our positions, minus the gradient of U, okay, with respect to Q. Or, so with the derivative of U with respect to how it changes around xi, okay. But our U would not change even if this particle, depending on the spring, it makes us a given path, but it goes back at Tn to the same position. And if this is fixed, let's imagine that this is fixed, then my the potential will be exactly the same because the length has not changed. That happens with gravity because gravity, okay, there's an associated potential associated to the height, okay. So if I go to the same height, I will have the same potential energy, and the force that is being created is, so to say, conservative. If this is with no friction, but if we have friction, we have also spent some energy, so maybe that our elastic potential, it only depends on the position, but the total force that we have, we're introducing a new force that is when we have C different from 0, the total force that we may have, and we add this L with 1 due to our dissipation, okay, at L0 it would not be preserved. Okay, with these frictional forces we can associate a potential, but which is non-conservative. Okay, so our depending on the path that we follow, we have a different result on the forces. So it's proportional to this velocity, and we may may have with a fluid, also with a solid. Interaction with a solid is a similar or interaction between solids. We had this example, so we had this particle that it's being on a substrate. So in the same manner, we may have this is moving on this direction, so we may have a force that is minus C by V, and that would be our frictional force. Okay. So interaction with fluids or with solids also as well. Then that's how it's happened, that it slows down our velocity. So for a free falling body, that's the case, or for a pendulum also. So that gives a little bit more realistic. Things do not oscillate with the same amplitude forever, but the amplitudes start diminishing, and is due to these type of forces. And these in reality, they are always there. We may neglect, so depending on the amount, or we may impose them. So our numerical algorithms that we had, some of them dissipated numerically the energy, but in this case, this is a physical dissipation that we are introducing. So even if you use an energy preserving algorithm, if we have this physical dissipation, energy, okay, will not be preserved, okay, because we have this physical loss of energy, okay, and our algorithm should also reflect that. All right, so how our equations are changed. So we have the same Euler-Lagrange equations, and we have this is not equal to 0, but equal to our frictional forces. And we can, one way of modeling that in order to use the same time integration algorithms that we have, is let's modify our potential and have the same elastic potential, but have a force that is proportional to the velocity, and dot multiplied by our generalized positions, our Q. Okay, when we do the derivatives, so note that here we have this modified potential, what we have as a new set of forces. Okay, our gradient, so the total forces that we have will be the gradient of U. We will have the gradient of our elastic forces that we have here, plus the gradient of this with respect to Q. Okay, just doing the partial derivative with respect to Q and not Q dot. Then we will have C by Q dot. Okay, and this will be our elastic forces that we had minus that, and here we have minus the frictional forces that we also had. Okay, so in total, this is, in fact, this is minus. We have the gradient is equal to minus the total force. So in that way, we do exactly as we do, and we use an artificial potential depending on Q, but also depends on Q dot in this case. Okay, and this is due to our frictional forces that we have. Okay, so in that way we leave everything unchanged in our Euler-Lagrange equations with a modified Lagrangian, okay, which is the kinetic minus the modified potential. And then looking at the preservation of the total energy with respect to that modified potential, then we have the time derivative would be equals to velocity by mass by velocity dot plus the gradient of U. If we look at our equations with respect to the h, and h still, and here our h is equal to t plus u, not u star. Okay, so from our equations, our h dot would be this velocity by mass by acceleration that we have here, and the gradient of u. From our equations that we have, in terms of the gradient of u, it's equal to the gradient of u star, which is equals to our velocity. So this is equal to minus m by v dot, but in addition with this term here. Okay. Oops. Our Euler-Lagrange equations are stated in that manner, equals to 0. Then we have that m by v dot plus gradient of u plus the gradient of the contact, this is equal to 0. So if our h dot is equal to velocity transpose of mv dot plus the gradient of u, because we are counting just for the elastic energy, the same as before, we don't include our frictional forces here. So from that equation, this is equal to minus v dot plus the gradient of u of the contact that we have here. The gradient of u of the contact is equal to the cq dot that we have, or the velocity. If we work with generalized coordinates, which are the Cartesian coordinates that we have, then we have minus c by vt v. Okay, and this is something that is always negative. Okay, it's the square of our velocity. This way that it finishes to right. Then minus c and the modulus of v square, which is always smaller than 0, right? So we see that h diminishes. So h cannot be constant. If we have frictional forces, my total energy measured as kinetic plus the potential of elastic forces is going to diminish. We call this as the dissipated energy, okay, or minus d dot, okay, which is the dissipated energy. Energy always decreases, and the dissipated energy is always positive. Dissipated energy is d dot itself, which is always going to be positive, right? So what is not preserved is h, but it's h plus d. Okay, if we write it as h plus d equals to 0, okay, then it should be preserved. And the algorithms that we can design is those that preserve the energy as we had before, plus this quantity here, right? So if we have now, and we use an energy momentum then we would use the discretized gradient, and it makes sense to use a discretization of the velocity such that our dissipated energy at time n plus 1 is equal to the dissipated energy at t n. Okay, this is exactly the same as having that my c by the norm of v n plus 1 is equal to c by the norm of v n squared. Okay, so in fact, usually these algorithms that use a discrete gradient of our potential energies, and remember that what we're using is that our increment of velocity would be n plus 1 half what's equal to the increment of our positions q divided by delta t. Okay, we had this interpolation here. So in general, we also use that the velocity v dot was the increment of the velocity. So in general, they also it's easy to implement strategies so that this is also preserved, and so they preserve the total energy, including the dissipated energy. Okay, so energy of the system plus dissipated equals to 0, and this guarantees that your dissipated energy will be always being positive, as they should do. You're not expecting that measuring the energy of a system with friction that the energy would increase, or that it starts accelerating, or that its rotations start also rotating faster and faster. So that is not what you would expect. Right, this is easy to include. So in the code that you have, in fact, is not much of a nuisance. In fact, including this additional term, okay, in our Euler-Lagrange equations, is nothing else that included on the right-hand side minus c by the current velocity. Okay, and the linearization of that in the Newton-Raphson is pretty immediate. If we use like an algorithm like this one, okay, that most of them they are using. Right, so no much of a trouble. If we're using explicit algorithms, so we may have this as Vn, and including the frictional forces at time n, and then keeping the algorithm explicit at the same time. Right, so with that we also have rigid bodies. We have also frictional forces. Okay, so embedded in a fluid. What we are not modeling is the effect of this motion on the fluid. Okay, of course the fluid is also moving, and it's also dragging part of the fluid and having inertial forces of the fluid. We are neglecting all that here. In a simple first case scenario, we just want to give the influence of the fluid on the particle. Okay, but without modeling the fluid itself. Okay, that may change slightly the motion of the particle. If we include also the motion of the fluid and then the feedback that it gets into the velocity of the particle due to the motion of the fluid. We are not dealing with that. That would require modeling the fluid, which is another story, more related with the first topics of this subject. All right, we may have also some simplifications. Okay, some of these simplifications means that we have a central field potential. So the same way that it depends on L, it depends on L. So we may depend also only on R. Okay, this is the case in astrodynamics. Okay, we have a center, we have a mass. Okay, and our particle. In fact, we have a potential that just depends, and this is as if that would be fixed, and our potential just depends on R. Okay, so this is very similar to what we had for the two masses, but in fact the two masses could move, okay, in parallel. It just depends on the length between them. In this case, we are having a potential with respect to a center, and seeing how this motion will be when it moves, but having a potential that it's only depending on the distance. That would be gravitational forces or interaction of one body, okay, with a beak on the body that does not move. Okay, in that case, what we have is that our position is the distance small r by the direction of the body, is ER. Okay, so we split our position Q as the position along the axis of joining the center with the particle and the orthogonal vector. Okay, so it only along this axis, which only have components along ER. Then the acceleration, we need the time derivatives, and here we have time derivatives of r dot. Okay, so we have r double dot with the second with the acceleration along ER, but also we need the time derivatives of this vector. The time derivatives of this vector, it depends on theta dot. Okay, so we have a term that also includes this theta dot also here, right? So what we are using in this case is that E dot, okay, our axis is just due to our theta dot r and along E theta. Okay, so it has just a component E theta. This is my theta. So when theta changes and r changes, okay, this can only rotate. So it's just filling the rotation of theta. In fact, this is a vector, and that we shouldn't have any r here. Let me remove that. This is when we have the distance also involved, but this is not the case. So we have theta dot by E theta. Okay, so the derivative that we have is how much is rotating, and the rotation, okay, as we have a theta dot, then it only has a component along this direction. Okay, by doing that, okay, we will have also a component along E theta. Okay, by doing the second derivatives of E dot, we will have our theta double dot, okay, multiplied by r and by E theta, and also the cross terms that we have, okay, because we also have derivatives of E r's, okay, and also the derivatives of E thetas, okay, which we have not derived here. Okay, when we have the first derivative, we have E theta, then the second derivative, we have theta double dot E theta, but also the time derivatives of E theta, which is along ER. Okay, so by doing all that, we end up by how my positions in terms for a particle Q in terms of r theta, how it's going to move. Okay, how its derivatives are going to change. In this case, E dot, okay, as we see, will be a theta dot, but the direction of minus r here. A way of deriving this E dot theta. So by using this and having this expression, we have this final expression of Q double dot. So due to the conservation of angular momentum, okay, the angular momentum is mass by the angular velocity, okay, and the angular velocity of that point on that direction would be theta dot by r, and the position is r also along this direction, so we have this r square here and multiply by the mass of that. So the conservation of angular momentum, we have that this should be preserved, and the equation of motions in fact is the time derivative of j equals to 0. The time derivative of this term is again having m r dot double dot, okay, minus this term which we measure, okay, the derivatives along this direction er that we have. Okay, so we can modify our potential, and we can have a modified potential which is this one that we have, ur plus, okay, this an artificial potential that we construct such that this equation can read in a simple manner. Okay, so that the derivative of VR would be ur, this term, and the derivative of this with respect to r, we will give rise to this other term that we have here with this definition of j. Okay, you can check that, in fact, how this is going to modify with j square, which means this term being a square here. Okay, so we build this modified potential, right, and then build in a simple manner our equations of motions instead of having to use this equation here. Okay, this in that manner it's very much as we have as the Euler Lagrange. Okay, this we miss something of the Euler Lagrange. We have just gradients of our u, in our case a scalar r, and we have mass by acceleration. So we want to write an equation with just mass by acceleration plus gradient of a potential, and that motivates the definition of that potential. Okay, I leave as an exercise driving why when we build this v we end up by having such an equation. It's just simple derivations, replacing j and doing the gradient of this v with this replace j, and you will get this term also here, right? So this is in fact, when you have a central field, you can go directly to build the angular momentum divided by this factor and write in the same as a 1D problem as a function of our r. Okay, so what we are doing is getting rid of the angular velocity of thetas. We forget about thetas, and we have an equation of our particle with see how it moves with respect to its position along this axis that we have here. Okay, and r being the distance from the center that we have, okay, up to here. Okay, and that will be our distance here for this particle. Right, so with that we also can use the same algorithms that we had. We might use them here, okay, and building for each time we measure also we need to measure this theta dot in order to have this j dot. Okay, but we don't have derivatives with respect to theta. That's the advantage that we have here. Okay, you can apply this, okay, for the Kepler problem. One direct application in the Kepler problem, our potential is just inversely proportional to r. Okay, so the forces will go to infinite as we get very close, and vanish to zero as we get far away from the center position. Okay, with that that will be for the Kepler problem, something like that. The force is minus the derivative. We have a minus in fact here because our potential is minus, such that our force is minus the derivative. We have a similar aspect. Okay, and would be also vanishing and with a similar trend like that also. Oops, sorry for my drawing, but it's doing a little bit crazy things today. All right, so we'll meet tomorrow. This is for the angular for bodies with just radial symmetry, as we have here.